I'm talking on retrieval augmented generation. That's a really funny word. How many people have heard of RAG or RAG AI before? Just a few. Well, not only did RAG not exist as a technology 1 year ago, but as hard as it is to believe, ChatGPT did not exist 1 year ago. 1 year, ChatGPT was released on November 30th, 2022. So last year when I came up and spoke, I spoke about AI, of course, a lot. Our H100 was just launching into the marketplace, entering full production. Today, it's, of course, in every CSP cloud, many on-prem systems deployed internally at NVIDIA and many of our large customers, almost all of them in conjunction with DDN. But we're here at Supercomputing, right? And so I want to tell a little bit of a story and a little bit about how this technology, RAG and generative AI, is really changing compute models, not just in the data science space, but all the way back into what so many of the traditional customers, if you've been coming here to supercomputing for 5 years, 10 years, 20 years, scientific computing, and GenAI is equally applicable there. And a great story, and I'll explain on how GenAI is changing the world from retrieval-based computing to generative-based computing. If you think about it, since the IBM 360 mainframe was launched a little bit more than 60 years ago, we did retrieval computing, whether on a green screen or later a PC or a cell phone. Think of what you do. You're flipping through some images, you're accessing the menu at a restaurant, you're pulling data, retrieving it, often from a DDN file system, from DDN storage out there in the cloud, in your data center somewhere. That world is changing, right? And it's changing. Retrieval-based computing is still there, but we're shifting to a world of generative computing. And the best example I can give is not in the photo that Alex showed, but if you go outside and look at the poster there that has my face on it, the DDN loved my headshot from SC23. And so they said, can we use that? But all the other shots were full torso shots. So they actually used one of the public generative AI tools to generate my torso image based simply on my headshot and some other pictures they found online of me and said, show Marc's face with him wearing a black polo shirt, which I often wear, NVIDIA black. And it came out pretty good. And so think about how that worked. My headshot was sitting on some DDN server somewhere on their campus, right? And it retrieved that. And then it went out to the cloud and it retrieved an AI model that said how to generate other parts, right? How to expand that image. And that AI model that it retrieved, compared to all of the pixels it would have taken for my image, relatively small. And right there on the endpoint, whatever device the DDN marketing team was using, it generated my full torso picture. Now, DDN doesn't have to worry. They're still going to sell a lot of storage for retrieval-based computing. But in this new world of generative computing, the storage will also be needed in other places. And in fact, Alex had edge computing there on it. And things like the new NVIDIA object storage are actually amazing for generative computing. Right? Because think about it. I think probably later James or one of the people will go into full, technical detail on NVIDIA, but one of the great advances are they're taking that object storage that you think about sitting in the data center, right? And they're actually moving it out to anywhere. to the edge, to lightweight devices. Some of their devices will be based on NVIDIA technology in the system. I'm not sure exactly which ones are announced or not, so I'll let them go into the details, but at least, certainly if not in the public and the private roadmap, they can go into how NVIDIA plays into Infineon. So GenAI is really going to change scientific discovery. It's going to put new demands on storage. Secondly, sustainable computing is equal to accelerated computing. This is something NVIDIA has been saying for 10 or 15 years, is we've devoted our company to building the most energy efficient computing possible. And 10 years ago, 5 years ago, people would say, oh yeah, but that GPU, it's 200 watts and the CPU is 100 watts. How could a 200 watt processor be more sustainable, more efficient than a 100-watt processor? Well, just look at any of the benchmarks, right? From top 500 to MLPerf. It's not just, I'm not just limiting this to NVIDIA GPU, because you have many GPU choices today, many accelerated computing choices. But today's computing cannot be done in a sustainable fashion, ever increasing large swaths of it. Dan Stanzone at Tech was today in our special address and talked about how their new system using Grace Hopper is a medium-sized system by supercomputer standards, but they view that as the gateway to their next supersized system, as Dan said, U.S. Congress pending, funding of that system. So again, I think that sustainable computing is very much a full-stack story, not just about the chip, but how you architect the system, deploy the system, and the storage. Retrieval versus generative, I talked about that. In full stack, right? Again, people say, how could an NVIDIA GPU perform so well, right? Why are all the new supercomputers, the first exascale system in Europe announced this morning using Grace Hopper technology, right? Because it's a full stack problem. And we're just not just accelerating at the chip level, but at the software level. In fact, we're a little bit bigger than DDN, but compared to other tech companies, still relatively small, about 25,000 employees, 21,000 in R&D, product engineers, and only about 1/3 of our product engineers work on hardware. About 2/3 of our product engineers work on software. So again, I thought I would talk, since it is supercomputing, of a couple of big systems. There were 2 EOS systems that we talk about. This is the one that's on, this is the one not on the top 500 list, but this is the one on MLPerf list that was announced last week. In the MLPerf listing, we call it EOS DFW. You can guess what the DFW stands for, is the data center that it's in. But this is 10,752 H100 GPUs with Intel CPUs in an HGX platform. I'm told, I'm not sure if there's anyone from Intel marketing here, but let the record show that somehow in the way these events get funded, we're using some Intel funding as funding NVIDIA to fund DDN. And so Intel is a co-sponsor, and we very proudly use Intel CPUs in our DGX H100, as well as many of our partner HGX systems. So this system is all based on Intel's CPUs. It's powered by DDN storage. I think we have 40 of the latest DDN AI 400 appliances powering this. And again, just a fantastic system. Broke 6 new world records for MLPerf. You say, well, MLPerf, it's a little calculation. When you're training these big models, I get it. You need to read everything in at the start, but why is storage so important? Well, think about it. 10,752 GPUs. Now that we're done using it for MLPerf, we're training our next generation NVIDIA large language model. we expect, I won't say exactly how long we think that's going to run to train it, because that would give away some of the size of it, but it's going to run for more than a month on 10,752 GPUs. You know something's going to happen, right? You don't want to run 3 weeks and then have a GPU fail. So what do? We're still doing checkpointing, right? And you need to checkpoint often, because 10,752 GPUs for 1 hour, and you can go look up, what the price tag is for any of those GPUs at Lambda Labs. One of our other partners is now one of our top H100 cloud providers, and that's a lot of money to waste an hour of time. So we checkpoint very often. Checkpointing, of course, is all going back to that DDN storage. If you have an error and you need to restart, it's coming off of that DDN storage. This is where you get double your money back. Those 10,752 GPUs, they actually cost more than the DDN storage by quite a bit, right? And think about it, you're checkpointing every 30 minutes, maybe every hour, and that time savings pays for itself on just checkpointing. And I know I've seen some great DDN slides on that. So there's the 6 new world records, again, top of class in all areas. This is an amazing slide. The first exaflop AI systems were the Summit and Sierra systems, deployed about 7 years ago now. Summit is still amazingly on the top 10 of the top 500 list. It was just released this afternoon. I hope it was released. If it wasn't released yet, scratch that from the record. But Summit is still on there. Today, a number of systems that are deployed, Leonardo in Spain and others, are in the multiple tens of AI exaflops. And in the next year, in 2024, we'll be deploying over a combined 200 exaflops of AI supercomputers, simply in scientific computing centers. I'm not counting here the many tens of thousands of GPUs going into the cloud, right? The Lambda Labs H100s are not in here. These are just in scientific computing centers. So by the end of next year, NVIDIA's estimates are about 350 exaflops of sustainable accelerated computing, AI exaflops in scientific computing centers. Now, why? Is Dan Stanzone turning over his system just to run data science? Of course not. All right, it's because the AI is being used in that scientific computing. Now, of course, this was a system that's been long in the making, the Jupyter Booster in the Jülich Supercomputer Center in Germany. So this system was announced several weeks ago, although we didn't share, Jülich didn't share the exact details. So Thomas Liepert, the director at Jülich, has been working with us for many years. They had an earlier booster system based on our A100 technology, but this one is much bigger, 24,000 Grace Hopper systems, close to almost 100 exaflops of AI compute in the system, and 1 exaflop delivered HPC performance on top 500 when it gets built next year. That's the goal for that system. So again, we're super excited about that system. So how do you build a large language model, a multi-domain large language model for scientific computing? There's lots of foundational models that you can start with. GPT-3, GPT-4, NVIDIA's NeMo model, Llama 2 from Meta is a popular one. There's many of those. And most HPC centers are not training new foundational models from scratch. That's probably what the Jupyter Booster, some of the largest systems, will be used to train new foundational models in new spaces. But most people, right, you can do a lot with ChatGPT and OpenAI, but a lot of people need to further customize and provide more customizations that are available through the rather simple APIs and customization tools, these sort of public models that really focus on, again, we love ChatGPT. If you can use ChatGPT, please go and use it because it runs all on NVIDIA technology. Every time you put in a query, my wife's new car is integrated in with ChatGPT. You can ask, it runs the Mercedes dashboard, and you can say, "Hey Mercedes," and start a conversation with ChatGPT. So I'm driving along with my wife, and she's like, "Why do you keep talking to the car?" I go, "Every time I talk to the car, it's like 3 cents to NVIDIA." And so, but anyhow, that model customization, right, is, again, there's many different tools being developed every single day, every single week. NVIDIA is taking all of the best open source tools out there, as well as our own tools that we're developing, and we're building them into a product we call the NeMo framework. And again, this is all of the development on this is optimized, benchmarked on our internal systems running DDN. We have now the Eos ML Perf system, 10,700 GPUs. We have our Eos HPC system that's on top 500 that has about 3,500 H100 GPUs in the system, and about a half dozen other internal clusters using DDN storage technology. So a number of different fine-tuning steps that are happening. And as great as OpenAI and ChatGPT is, right, there are many times when you can't use it. Right? Either you can't use it because you don't want to upload your data to it. Again, the model is generative, right? Every time you use ChatGPT, you're in effect making it better. And if you're trying to make it better for you and don't want to make it better for one of your competitors, then again, you may have some concerns over doing that. You may want to do that in your own environment instead. So anyhow, besides the generative AI approach, there's a final step to this, the retrieval augmented generation. So how are these things playing into scientific research and discovery? And what are some places that language models, large language models, are being used in the scientific domain? One of them is simply in physics-based machine learning. And again, if you think about it, with our modulus framework, you can train physics-inspired neural networks. And this only makes sense, right? If you can train ChatGPT to answer a question that you answer, and again, remember, ChatGPT is optimized to be very good in the most general sense, because what sorts of questions is ChatGPT trying to answer? Well, basically any question, right, that you can answer it. And so in physics-based ML, we're actually training a deep neural network not to answer any question, but to help understand the laws of physics. Right? In most of the supercomputer centers around the world, most of their time historically has been used calculating, simulating the laws of physics. Right? And this is actually a great problem to apply generative AI to, because of course when you simulate the laws of physics, right, it's a simulation. Right? You're using the laws of physics, but you don't really know if that physics that you simulated is actually how the clouds are going to form in the weather model in the real world, which is why you use ensemble models and put together multiple models. But again, by using generative AI to guess the laws of physics instead of calculating the laws of physics, you can do tremendous speed-ups to simulations. We worked with ECMWF on one of their large language models, and we're able to, under our Earth-2 project, accelerate it 44 times simply by adding a modulus front end to it. NeMo is, of course, our generative AI model. Again, so think of NeMo as something like Llama 2. It's not a proprietary model, right? You can go through, modify it, use it internally, use it for your own systems. Again, similar to an open source model. And finally, BioNeMo. In our special address this morning, Kimberly Powell, our VP for Healthcare, talked about how some of the leading drug companies around the world are using BioNeMo to generate not text, but generate new molecules in the search for drug discovery, building new vaccines, etc. And we'll have one of our joint users from Roche up speaking later, and he'll talk a lot more about that whole area of BioNeMo. So, again, what are some of the guidelines for storage performance? I saw a release from another storage partner the other day, and it said, we're using, our system is set new world records, providing 25 gigabytes a second of performance to serve up 65 accelerators. Now, I'm not sure what 65 accelerators they used, but they certainly weren't the H100. Because look at our recommendations. This is for a single node read on an HGX or DGX H100. So 8 GPUs. We recommend 40 gigabytes per second read performance, 20 gigabytes per second write. So I actually commented to our account manager for that particular storage company. I said, someone should go and tell them that what they're claiming is a world-class benchmark is about 8 times too slow for our recommendations. But again, they might have been using someone else's GPU that wasn't from NVIDIA. It wasn't clear in their press release. But if you're going to use NVIDIA GPUs, again, I always recommend, I say, look, I'm not up here as an OEM partner of DDN because they resell DGXs or because we recommend and ship DDN. I'm up here talking as a user, right? We're one of the largest enterprise users of DDN. I don't know the exact stacks of what. I'm sure there's supercomputer centers that have many, many petaflops of it, but from an enterprise user, I'm sure we're up there in the numbers. DGX SuperPod is, of course, our predefined product for building an AI factory, right? This starts with 32 DGX nodes. It's a full-stack optimized solution. Includes 8-rail InfiniBand fabric for the compute, includes separate InfiniBand fabric for the storage, includes DDN storage, fully optimized. We run MLPerf, we run HPL on it before we deliver it, and then we support it with Tier 1 support. You can simply buy the DGX SuperPod. If you have a problem, you can call DDN, you can call us, no finger pointing, everything's handled in the back end. And so Jensen's been very busy, and so he wants to make everyone else busy. So we're rolling out a new product, a new offering for what we're calling NVIDIA Cloud Partners. We're not announcing it today, so I won't say all of the details, but it's basically to take the DGX SuperPod design, this end-to-end solution, and deliver it with other OEM HGX servers through all sorts of cloud providers like Lambda and others. I'm sure Lambda will be part of this new program when it's announced. And so again, my team running solution architecture and engineering will be working with all of these new cloud providers to make sure we deliver that end-to-end DGX SuperPod experience on OEM-based servers, ODM-based servers that cloud providers are using, really expanding that experience to a much broader user base. So we're very much looking forward to working with DDN, and we'll of course have certified, just like we have certified networking, we'll have DDN as a certified storage partner on that most elite program that we roll out. Now, some people, may say, well, you're at 700 watts for your GPU today. The Grace Hopper module can be up to 1,000 watts. And again, because this is not an NDA presentation, I won't tell you where that's going, but it's not going down in future versions. So how do you cool these sorts of environments? This is sort of the next step in sustainable computing. This is the next step in end-to-end full-stack architecture that we're working with the entire ecosystem, the storage providers and others. And so, again, we realize today many enterprises in their data centers, and even many cloud providers in the data centers they have, their existing data centers don't support water cooling out on the floor. Obviously, at some point in most data centers is getting to water, but not always on the floor. So we're designing sort of that next generation of SuperPod to go beyond the server with the GPU, networking, and storage to encompass the full physical design, the CDUs, and everything. So we'll be using direct liquid cooling for that. We're working with all of our ecosystem providers from all of the server vendors to make sure that they support direct liquid cooling. But again, that's going to be for the Grace Hopper module, the GPU and the CPU. There's other components, including the storage, right, that don't necessarily make sense to do direct liquid cooling on. So you need to support hybrid designs. And how do you support that direct liquid cooling without forcing everyone to move to a new data center? So we're taking this liquid to air sidecar approach, right? And again, using Omniverse, which is our package for collaboration and building digital twins, we actually built up the virtual design of this system. And again, next to each rack with those 1,000 watt plus Grace Hopper systems in it, direct liquid cooled in the future, right, from various OEMs. We'll have a liquid to air sidecar. So it's a little bit backwards. That'll do direct liquid cooling, and then it'll take that liquid and it'll turn it into hot air to go into the data center. But it lets you benefit from a single node that's direct liquid cooled in an air-cooled data center. So we have a nice little simulation here that'll get started in a minute. So this simulation is all done in Omniverse, and this is a physically accurate simulation. So all of the CFD is not just pretty pictures, but is actually done with Modulus, and with, in this particular case, was done with a CFD tool called Six Sigma. So you see there the DGX H100 systems, putting, in this case, 4 in a rack, and then you see the liquid sidecar, the air to liquid sidecars in the center. And again, we're still working on the simulation. So again, but it gives you an idea of some of the different capabilities. And again, what you're seeing here is many different individual representations of the product being brought in to Omniverse. You're seeing CAD drawings, you're seeing CFD simulations, you're seeing the airflow simulations, also CFD, going through and being brought in and visualized in one tool. So in the future is we're designing these DGX SuperPods and working with our OEM providers to provide SuperPods. We will set up and simulate these hybrid air-water cooled systems before we ever show up into your data center, making sure that, again, just like today, you have that full stack hardware and software extends to all of your environmentals. This goes on and on, I think, so I'm going to skip to the next one. So, of course, where we really want to get to, and we've built out systems already like this at NVIDIA, is as you get liquid out into your data center floor. And again, many data centers have liquid cooling, liquid pipes already underneath the floor, even if they're using standard air-cooled systems. So with direct liquid cooling in a liquid to liquid CDU, we can support up to 120 kilowatts in a rack, which will then use air cooling for the non-DLC components and liquid cooling. Now, in this particular case, this is not just showing you the virtual or digital twin. This will show you a side-by-side view of the real physical pod. And you say, well, what customer bought it? The customer for the physical part is actually NVIDIA. In one of our factories, we've built up, because we're building our own experimental direct liquid cooling systems today, and we're building the HGX direct liquid cooled for some of our OEM partners that already today are shipping direct liquid cooled HGX systems. And so Jensen likes to say it takes a supercomputer to build a supercomputer, right? So as we build the HGX or DGX nodes, we're actually going through and installing them in this fully liquid-cooled environment in what we call the running room, and running multiple days of sort of burn-in tests. So not only, and this is again testing the full stack. So when you install that system, connect it up to your liquid cooling, because we'll have simulated not just this particular system, but this particular system has the liquid cooling of this particular facility. But in Omniverse, we'll take your cooling tower, your water temperature, your air cooling systems, and we'll simulate all of that in Omniverse. Because again, you say, well, how can you do that? There's so many different tools out there that are being used. Well, again, today, we're trying to get full coverage of all of the top leading tools and CFD analysis and other analysis, so we can build digital twins of your next generation direct liquid cooled system before it ever goes out. And again, out of here comes a tremendous amount of test data as well, and great applications, I think, for some of the new DDN object storage. And think about that, building that digital twin and then going through and having that delivered as part of the solution. So as you're monitoring, running your system, 1 week, 1 month, 1 year into it, something changes, you can just pull up your digital twin and say, hey, where's the disconnect or where's the difference going on here? I thought I would highlight a few customers using the DGX SuperPod and NVIDIA. Next year, looking forward, or maybe even at ISC coming in and showing some of the early direct liquid cooling examples. But this is one of my favorite, Naver in Korea. They were our first customer to deploy a full 140-way DGX A100 SuperPod, and they recently went in and expanded this system very seamlessly. It took just a few weeks to do the upgrade, and they expanded it to 280 DGX A100 systems with, of course, expansion in their DDN. So why did they pick A100 when H100 was already out there? Well, again, such a good product. In this particular case, they took a conservative approach, wanted to just double what they had, as well as then move on. You will want to move on if you're on the DGX A100. Ian Buck showed today in our preview the H100 today running MLPerf is running 11 times faster than the A100. At launch, it was about 6 times faster 1 year ago. How do we improve performance from 6x to 12x faster in 1 year software? And we showed some early numbers for MLPerf running on our new DGX H200 with increased memory, a new HBM3E memory, 18 times faster than A100. And then here's another customer from India. So CDEC is building India's foundational model in local languages, and they started off with 42 DGX A100s, and over the last few months also expanded this to 82, also expanding their DDN storage. So I think this repeat business really stands for, again, how customers love DDN and continue coming back and back again and again. And so with that, I'm out of time, but I think maybe I have a minute or two to take a few questions. We'll see how...
We have any questions in the room? Mark can answer them. We have microphones on each side here, if you want to raise your hand. I don't know. You covered it all. Okay. Pat.
All good. I was just wondering, like, how are you keeping the transceivers cool on the backside? Because those GPUs just pump out heat, and it's not good for the networking.
Yeah. So cooling transceivers is a important thing that you have to do. So again, this is the beauty of simulating all of the CFD and Omniverse. Before we actually go through and deploy that, we can understand exactly how that's going to be cooled. We're continually looking at, and again, a number of different ODMs provide different solutions with where you can put your transceivers at the front. So again, don't know what our future products will hold, but keeping those transceivers cooled is increasingly important.